All right, good morning, everyone. I'm Boyu from RWTH Aachen University from Germany, and today I'm going to give a presentation with the topic Integrated Study on Chromium Aluminum Carbide Coated Zirconium for Accident-Tolerant Fuel Systems. And this presentation will be divided into three parts. And first of all, let's go to motivation, targets, and plan. So what drives the carrying out of this investigation is the safety issue of the nuclear power plants. A very sad example is the Fukushima Daiichi nuclear disaster that happens 2011. It happens because of the failure of the cooling system after the occurrence of a tsunami, and the zirconium cladding tubes was oxidized at very high temperatures in the reactors and finally lead to the hydrogen explosion. And from this disaster, we learn a failure mechanism of the cladding tubes in nuclear reactor. Is the loss of cooling agents. And another main failure mechanism is the reactivity initiated accidents. And no matter which types it was, it tells us a very important lesson is the design of the cladding tube, especially at the loss of cooling agent scenarios, is very important for nuclear power plant safety. So we have developed a new cladding tube system to assist for the application in this loss of cooling agents new scenarios, and we aiming at researching the fundamentals for the safety assessment, namely the failure mechanisms. And in this investigation, there are two materials involved. One is the zirconium, which has long been used in nuclear power plants as the cladding tube materials because of its very good ductility, very good thermal conductivity, and low absorption of neutrons across section. And another material is the max phase material, which is actually a ceramic materials, and M is a transition metal, and A is actually a 3A or 4A group element, and X is denoted as carbon or nitrogen. So what we do in this investigation is, first of all, we propose this cladding tube concept, and then we do the basic mechanical characterization of the involving materials, and we identify the failure mechanisms of the coated samples. And coupled with the numerical simulations, we can establish a microscopic failure criterion that can facilitate the safety assessments of these new types of cladding tube system. So following this routine, what we have achieved is, first of all, the basic mechanical property characterization. So for the zirconium, we have carried out uniaxial tensile tests on standard dot ball samples and also shear samples. And based on the flow curve, we managed to characterize its mechanical properties and also fit its flow behavior based on the Swift hardening law. And for another material, the max phase material, we have chosen its member, which is chromium aluminum carbide. And we did a nano indentation test, and coupled with the simulations, we managed to characterize its mechanical properties and also fit its flow curve based on the Swift hardening law. Then, and also I have to mention that for zirconium, its thickness is 0.7 millimeter, and for the coating, we have finally determined to be 3 micrometer. Okay, so next step is that we manufacture our zirconium sheets into several geometries because we want to cover a wide range of stress states. And then we coated the chromium aluminum carbide onto these manufactured samples. And then we put the coated samples into a bending modeler and inserted the whole bending modeler into the chambers of SEM. Then we carry out interrupted institute 3-point bending test to record how our samples were deformed during the test to identify its failure mechanism. So based on the SEM images we have recorded, for example, here, use a sample without any notch for explanation. So when the displacement of the loading rod reaches a value of 2,500 micrometer, cracks appears in the coatings, which means that the cracks fracture and fail already. And we continue the loadings, and when the displacements of the loading rod reaches the value of 7,000 micrometer, cracks propagates from the coating to the substrate. And this phenomena were also observed in other samples with different geometries, for example, the bivital notch, univital notch, and semicircular notch. And the differences only lies at the displacement when the cracks initiates in the coatings and when the cracks propagate from the coating to the substrate. So based on our observations, we have identified the failure mechanisms of this coating system, which is the cracks initiates at the coatings, and with further loading, it propagates from the coating to the substrate. Then comes the next question: at what stress states that these two critical moments happen, and how can we define these two critical moments? And due to the difficulty of recording those stress states in the SEM, we have used the alternative method, which is the numerical simulation method. And what we did is follow the routine at the right side. So we carry out in situ 3-point bending tests and also the simulations without coupling any failure criterion yet simultaneously. And we compare the experimental curve and the simulated curve, force and displacement curve. And we extract the stress-related parameters at the critical moments, including the equivalent plastic strain, the maximum principal stress, stress transitivity, and load angle parameter. And we establish a failure criterion, and we calibrated the corresponding parameters. After we finish that, we run another round of numerical simulations to validate our models and also our parameter calibration. So following the routine, what we do, first of all, we still need to consider one very important thing is the strain differential effect, which refers to the asymmetric responding to the external loading and tension side and a compression side, and exists widely in HCP structured metals, and zirconium belongs to HCP structured metals. And also during 3-point bending, that tension and compression exist simultaneously. So it reminds us when we run the simulations, we have to couple these strength differential effects into the simulations. So we have chosen the use criterion, and there are 3 parameters A, B, C for us to calibrate. And we check our experimental result, and we also refer to the work of other people, and then we finally determine a group of ABC values. Then we also investigated the mesh size effect because there exists a significant differences between the thickness of the coating and substrates. And we actually adapted 4 types of mesh size, refers to the coarse, middle, fine, and gradient. And we compare the results of the critical stress states at the critical moments of the critical elements. And we figure out there exists no significant differences. And to increase the computational efficiency, the coarse mesh was finally adopted. So we run the simulations without coupling any failure criterion yet. And what we have found, then when the coatings fractures, it fractures with a very limited plastic deformation. And consider the data scattering, we finally adopted the maximum principal stress criteria combined with the Weibull distribution. And there are several parameters we need to calibrate. So what we do is that we calibrated the failure probability at the corresponding maximum principal stress that we have already sequenced that from the smallest one to the highest one. Then we can calibrate the corresponding parameters. We also consider 3 failure probability, which refers to 5%, 50%, and 95%. So at the right side shows the failure probability with the corresponding fracture strength, and also how the maximum principal strength involved with the stress transitivity and load angle parameter, and shows we managed to cover a relatively big stress state. So similarly, for the crack propagation from the coating to the substrate, that the substrate undergoes considerable plastic deformation according to our simulation results. And here shows our collected data at the critical moments. And here shows for all these 4 types of geometries, how the stress transitivity and load angle parameters involved with the equivalent plastic strain that indicates we managed to cover a wide range of stress states. And for this characterization, we have chosen the modified Boyu model. So in this model, it mentioned that when the critical equivalent plastic strength is reached, that the sample is damaged. And there are 4 parameters that we need to calibrate. So we calibrate these 4 parameters based on the equivalent plastic strain, stress transitivity, and load angle parameter that we calibrated, that we collected from the first round of numerical simulation. And we used the MATLAB to help us with the calibration. And at the left corner, that is the calibrated data. So now we have identified how our samples was fed, and what kind of failure criterion we should adopt it, and also we calibrated the parameters. So we run the final round of simulation, and we replicate the failure, the material failure that we observe in the experiments by the element deletion. So here shows a video. So first of all, that the cracks initiate in the coatings by element deletion, and then with further loadings, that the elements in the substrates were deleted, which means that the cracks propagate from the coating to the substrate. And if we compare the results statically, then we can see that we managed to replicate the curve, force and displacement curve, and also the crack initiation and propagation with a very good accuracy. So for simple sample, that is an example for presentation, and for others, they are the same. So from this investigation, what we have concluded is that, first of all, we define the failure mechanism of the coated sample is that the cracks initiate at the coatings, and then with further loading, that the cracks propagate from the coatings to the substrates. And we investigate the stress state effects by designing different kinds of samples, and we found that the notch design affects the moment when coating cracks, and when coating fractures, and then when the cracks propagate from coating to the substrates. And finally, we developed the macroscopic failure criterion and also calibrated corresponding parameters. We managed to validate this work by replicating the material failure that we have observed during the test. So that's my presentation today, and thank you for your attention.